Hello, my name is Wenceslao Cortez. I'm a postdoc at the KTH Royal Institute of Technology, and I'll be presenting work co-authored by Christos Verginis, myself, and Professor Dimos Dimarogonas, titled Adaptive Cooperative Manipulation with Rolling Contexts. So the idea with cooperative manipulation is that you have multiple robotic manipulators, each with their own mobile base, and they are working together to manipulate or grasp an object. So you can think of a scenario in an automated warehouse where you want to move or transport objects from one place to another. In this kind of setup, cooperative manipulation offers flexible, versatile way of transporting heavy payloads. And one thing that we want to look at here is this idea of rolling contexts. So a lot of the existing work looks at rigid contexts where you somehow have to have a rigid attachment at some point on the object where you can apply any force or torque. However, this can be hard to realize if the object doesn't have such a location where you can rigidly attach. I'm going to look for a more general setup where we have a rolling contact. That is, you only need some passive end effector to come in contact with the object, and that is sufficient to let you apply some force on the object. And so you have the cooperative manipulation entailing multiple manipulators working together to grasp the object instead of having each rigid attachment to an object. So this applies to more general objects because you just need to have contact with the object. And what we want to do is we want to look at uncertain dynamics because we don't know a lot of the dynamic parameters of the robotic agents or of the object that might be needed to be transported. So previous work, as I mentioned, a lot of it has focused on rigid contexts, but also some focus on having some knowledge of the dynamics or require some force or torque sensing at the contact point, or similarly knowledge of the object's center of mass. Whereas in this work, we want to look at cooperative manipulation with rolling contexts, so a less restrictive form without requiring force sensing. We want to look at how to use adaptive control to address the uncertain dynamics and object center of mass simultaneously. And as a result of looking at rolling contexts, we have another difficulty. We have to ensure that there's no slip so that we can actually hold the object throughout the entire trajectory. So to get into the problem formulation, here we have n robotic agents depicted in this figure on the right. And each agent has its configuration defined by Qi. We have the conventional Lagrangian dynamics, inertia matrix, Coriolis matrix, gravity torque. This term here is the torque applied on the joints of the robotic manipulator that is dependent on the contact force. So each agent will contact the object at some point, and there will be some force transmitted at this point, and that is what is mapped here by the agent Jacobian onto the torques of the manipulator. And finally, we have the control torques that we will implement, our control input to the system, UI. So just to take a little look at the agent Jacobian, it's dependent on the conventional Jacobian for a robotic manipulator, but multiplied by this matrix. Here we have the identity matrix, and what this term is, PFCI, is the location of the contact point for each agent. So with this, we can concatenate all the dynamics together to get a vector form of the robotic agent dynamics. We can do something similar with the object. We know that the center of mass is denoted by this bar. So x0 is the pose of the object, p0 bar is the position, eta is the orientation. And we can write the conventional Euler-Lagrange dynamics. We have, again, the inertia, Coriolis, and gravity terms. This term here represents the net force that's applied on the object about its center of mass. So again, we have the relation between the contact force and G bar, which maps that into the net force. So if you look more closely, the grasp matrix is composed of the concatenation of all individual grasp maps for each agent. And more specifically, takes this form similar to the agent Jacobian. We have the identity matrix here. And here we have the distance from the object center of mass to the contact point, which is also depicted in this figure. Now we set up the dynamics, but we actually have the assumption that x0 bar is unknown. That is, the center of mass is unknown a priori to the system. Instead, what we want to do is replace this with some point that can be detected, say by markers on the object or cameras that can sufficiently track an object configuration. So this will be denoted by x0. and P naught is the position, eta naught is the orientation again. So what can be done is we can perform a rigid body transformation. So here we're assuming that the center of mass is not moving, and we have the distance between the center of mass and this detectable point, P naught, written in the object frame. So when we do the rigid body transformation, we actually are including the center of mass terms into our new inertia, coils, and gravity terms. But as a result, we actually eliminate it from the grass map. So now the grass map, again, is a concatenation of the individual grass matrices. And we have this term, which is no longer dependent on the center of mass, but only the distance from the detectable point, P naught, to the contact point. Finally, because we have rolling contacts, we need to make sure that the contact points do not slip. This is eventually done by ensuring that the contact forces always remain inside a friction cone, which is depicted here on the right. The friction cone, for some fingertip touching object, is a set of all forces such that slip does not occur. And as is intuitive, the slope of this cone is dependent on the friction coefficient. However, this can be difficult to implement, and so what's typically done in practice is this cone is linearized. That is, that there's a inscribed pyramid that's used to represent the friction cone. We denote this the friction pyramid, which is written here. And it's simply, the main thing to point out is that we can write the condition that our contact force is in this friction pyramid as a simple linear constraint as shown here. And this represents a vector-wise inequality. So basically map all the contact forces into the friction pyramid and check that it's non-negative. Now we can get to the problem statement. We have some desired trajectory that we want the object to track. And we can define the error associated with the position and the error associated with the quaternions for the entire trajectory. So what we want is, under the condition that we don't know dynamic parameters of the agents in the object, we want to design a control law that asymptotically stabilizes the system about the origin, and also ensures that we don't slip throughout the entire trajectory so that the contact force remains inside the friction pyramid. The way to do this is we first couple the agent and object's dynamics together. So M tilde, C naught tilde, G naught tilde represents the coupled agent object inertia, coils, and gravity terms. And now we have the control input here that's mapped to the net force on the object by the grass map times the inverse transpose of our agent Jacobian. And what we've shown is that actually this system is still linearly parameterizable with respect to the dynamic parameter uncertainties. So that is, we can rewrite the left-hand side of this dynamics as a function of the regressor matrix, which we know, y naught and y, times all the uncertain model parameters of the system. So nu naught are the unknown parameters of the object, nu the unknown parameters of each agent. And so what we have is then what we're going to do is try to estimate these parameters online. So we have these approximations, nu hat and nu hat naught, and we can find the errors between the approximations and the true values as these terms here. So now we can get into the adaptive control law as written here. So we have our control torque. First, what we try to do is feed forward essentially the dynamics of the agents. Of course, these are uncertain dynamics, which we have to update online. And we also have a term associated with the manipulation. So this is split into two components, the FD and FInt terms. FD is is responsible for moving the object. So what we do is, again, in a similar adaptive control fashion, we try to feed forward the dynamics of the object, of course, with the estimated object parameters. And we have some feedback, PD type of feedback term on the error. So this is going to try to track the trajectory that we want. And FInt is used to make sure that we don't slip. This is telling each agent how to squeeze the object. So for some clarification, we're dependent on this term EV. This is simply the error between the object's velocity and an auxiliary reference written out here. So this is a fairly standard method in adaptive control to ensure stability of the system. So next we look at the internal force. So again, this term is to make sure that slip does not occur. What we're going to need is that it's in the null space of our grass map. So we'll look at this in the next slide. Finally, we have our parameter estimates here, nu hat and nu hat naught, and we need to update them appropriately. So we've constructed these update laws based on the system dynamics, but we've added something slightly different from a conventional adaptive control technique, and that's that we've used a projection operator. What the projection operator does is it restricts how much the parameters can change so that they always remain inside some bounded set. And more specifically, it means that the error of our parameter estimates are always bounded, and these bounds, ENU bar and ENU not bar, are actually defined a priori. So we know that the system will, the parameter updates will always stay inside this compact set. So to the internal force design, this is a novel approach compared to many of the existing works used in the robotic grasping community. And what we do is we separate fint into two main components, fint, which is the scalar term, and this L star. This RPC is simply a rotation matrix. So L star is associated with the direction of each internal force component. So we're just trying to minimize the overall squeezing term on the object, subject to these constraints. So this constraint says that we're in the null space of the grasp map, which means that we're not causing any motion. The internal force is not causing any motion on the object. We can only apply pushing forces on the object. And we always remain inside the friction pyramid. So once we have the direction of the internal forces, we then look at the magnitude. And this is where things become a bit different. We actually try to reduce how much energy is being used to hold the object by taking into consideration that we already have a force that's going to try to move the object. So looking at this term, let's look first at this K. K here is the mapping of the manipulation term that from our control law into the friction pyramid. And so what this kappa is saying is that if this mapping is positive, it means that the manipulation component of our controller is actually helping to apply enough normal force to resist slip. But if it's not sufficient, if it's negative, then we need to add additional internal force, additional squeezing to make sure that slip does not occur in the system. Okay, that's the main idea here. These other terms are for scaling and for robustness. But basically what we're doing is we're reducing how much each agent has to squeeze the object. So with that, we can get to the main theorem. We have a few assumptions to make. First, we have 3 or more agents which have nonlinear contact points. And basically there always exists a way to grasp the object. It's saying that the range of the grasp map intersected with the interior of the friction cone is not empty. This means that there is no slip that's going to, this means that there exists a way to grasp the object. We assume that our agent Jacobians are non-singular, so we have an appropriately defined reference, and the contact points do not exceed the fingertip surface. Finally, we assume we are not in a singular configuration with respect to the quaternions, and that the initial contact force is in the friction pyramid, so basically initially we're not slipping. So for some sufficiently large tuning parameter epsilon, which can be computed offline, the proposed control guarantees that we're asymptotically stable to the origin, and the contact forces remain inside the friction cone. So just a sketch proof of what's happening. Because the dynamics are continuous, you can actually show that the contact force, because they're continuous and the initial contact force is inside the friction pyramid, you know that for some instant in time, no slip will occur. And so what we can say is define this Lyapunov function, take its derivative. We see that in fact it's a negative semi-definite function, which is typical for adaptive control techniques of these types of systems, which means that all of the closed loop signals are bounded over this time interval. Now what we're going to see is what happens in the internal force. So we want to check that no slip occurs. So we look at the friction pyramid. We define our contact force here that's dependent on the components of our controller, and we move all the uncertain terms to H, which is in fact a bounded disturbance on the system, and we can upper bound it by this epsilon of H. So when we substitute this into this condition to check if the friction pyramid, the contact forces are in the friction pyramid, we yield this equation which needs to be satisfied, and via the internal force design, we can show that with an epsilon term that upper bounds this epsilon of H, again this epsilon can be computed offline, then we will actually ensure that our contact forces remain inside the friction pyramid. Now, because we've shown that the no slip is actively prevented, And that means that we can repeat this analysis and basically extend tau to infinity, at which point we can apply Barbalat's lemma for stability. It shows that, in fact, asymptotic stability is ensured. And of course, as a result, we have no slip of the overall trajectory. So finally, we get to some simulation results. Here we have three agents grasping a rigid box. So this is a cube box, again with rolling contacts. We give them a sinusoid trajectory in position and orientation. And as shown, we see asymptotic convergence to the origin. But let's see now what happens with the parameter estimates. As desired, we see boundedness in both these estimates with an a priori bound defined. In this plot, we're looking at slip. So the black dashed line is the required friction, the actual friction coefficient in the system. And each of these three trajectories show the required friction for each agent to apply its contact force. And so since each required friction coefficient is less than the actual friction coefficient, it means there's enough friction to implement the proposed control strategy. And finally, we have the bounded control inputs that give us the asymptotically stable system. So to conclude, we've presented a method of cooperative manipulation with rolling contacts. We've used adaptive techniques to address uncertainties in the dynamic uncertainties in the object and the agents. We ensured that there's no slip as a result of our controller without requiring force sensing or knowledge of the center of mass. So current work, which we plan to submit soon, is the decentralization of this proposed scheme, relaxation of singularity assumption, and addressing grasp reconfiguration, which is really tackling highlighting one of the advantages of having rolling contacts is that we can adjust the grasp online. So with that, I will conclude and take any questions. Thank you.